Today
Good morning,
we
sir.
will discuss transient water flow. Is precisely transient groundwater flow in rock and rock mass. So we should know the detailed procedure, how this can be done. One thing I want to give an introduction that this transient water flow system will be utilized, can be modeled very easily using the numerical models, numerical methods, and more particularly the finite difference. So we will devote one class on that, detailing that particular part, the numerical method applications. But the numerical methods is basically solving different equations iteratively, simultaneously, and converts the solution to get a finite solution. So that can be done mathematically, and same thing can be simulated using the software. How software can be used that we can later discuss with you. We have devoted few lectures on different numerical methods and their applications. So this transient water flow uh, is basically required for modeling the effect in slope due to the rainfall or rainfall precipitation. You can understand rainfall is basically uh, sometimes sporadic, sometimes very heavy, and somewhere it is not at all. So there is a different phases of the saturation and unsaturation of the rock mass layer. So this transient water flow system will model that saturation and unsaturation, how these things continuously originate and flow, and that simulation basically simultaneous solutions of those different situations is basically what we'll deal today in transient water flow system. So let us do that. So in transient water flow system, so in transient water flow system, you may ask, how does the mass of water stored in aquifer change? So there are two type of uh, aquifer we have already discussed. One is a confined aquifer, another is unconfined aquifer. So this compression is possible in confined aquifer because confined aquifer basically obstructed in the upper impervious layer and the lower impervious layer, and there is a possibility that it can compress. But for a unconfined aquifer, the water basically what happens when drains out from this pore to this pore, then actually water table drops, and water table raise means that those pores are basically filled with waters. So basically, if you simulate the things, you can understand. And this in this process, basically, there is no way to compress the water as well as the stratum. So the change of storage, the term we have already studied in the last class, can be rewritten as del Pn rho n dt. Okay. then you can differentiate between, because n and p is a different function. So n dp del t, p del n del t can be rewritten as. Now here, these del P del T basically indicates the density change of the material. Density change of the material. So if the density change in the material is basically, it indicates the compressibility. Due to the overburden pressure, it compresses. And del N del T is basically indicates the porosity change. N is basically the porosity. So del N del T in time scale, how much changing is occurring in porosity, that is basically. So the overall definition in the storativity index, when we have understand the specific storage, is basically of a saturated aquifer. The volume of unit water per volume of aquifer released from the storage for a unit decline of the, so 1 divided by 8. Take a example of this kind of system. There is a uh, head potentiometer surface it is indicating, and this is unit cross section, and there is a unit decline on the potentiometer surface. Based on that, for a confined aquifer, we must consider the compressibility. You can determine how much compressibility can be calculated. This can be, you can read it as compression of the individual grains of the skeleton. Compression can be of two types, because when there is a pressure is given on a rock mass, individual grains have a tendency to compress one upon another. But the grains, the smallest unit is basically incompressible. So what will happen? The smallest unit, the grain is incompressible. Then what will happen? In between the grain, there will be readjustment or realignment or rearrangement of the grain. And due to that realignment and readjustment of the grain, what will happen? Effective pore space will get reduced. Effective pore space will get reduced. So this basically the layer will get more compressed. What about the compression of the water? The compression of the water is basically the summation of these two, rho g alpha and rho g n beta. So what will happen in a rock? There is a load, overburden load, as well as the effective stress, that is the upward buoyancy force of the water will act on the same plane. Based on that, we can reformulate the same. So del T, sigma T is basically the weight of the rock and weight of the water. Weight, remember. On a rock mass, it is basically saturated, and it is a aquifer, and this aquifer is a confined aquifer. So what will happen if we draw system? Draw this system. We draw this system. Basically, if it is a confined aquifer, this is impermeable layer. So this is the confined aquifer. Now think about the water. Suppose the drains. Think about this system. How the water in aquifer stay and it look like, and what is the dynamics of it. What in the last slide we have actually talked. This individual grain, suppose this is a grain, rock particles or grains. This grain strength is very high, so it is basically incompressible. It is basically incompressible. But due to the overburden pressure, what will happen? The pores, space, and the grains will rearrange each other. So there is a tendency of this particle to get downward. There is a tendency of this particle to get downward. There is a tendency of this particle get down, and in between, what will happen? These effective pore space basically what I want to show you. This pore space, what we have, and this pore space is basically the space for the water to stay, or basically the source of storage will get reduced. Now, considering the earlier questions, what we have shown you, it is a del sigma t. This sigma t will act downward, basically the cell point of the rock, as well as always the water also have a weight, plus the weight of the water. Here it is basically pure weight of water. Now the next expression is sigma t is basically plus p. What is this p? P is basically pressure the fluid. Okay, effective pressure and the fluid pressure. Okay, basically the fluid pressure. This is maybe upward force, and this is the so now Now it is understood how the self weight is working on the aquifer. Is clear? Everybody, it is clear? Is it audible?
Yes, sir.
Yes, sir.
Now, when it is basically the expression now, when there is a pumping means there is a specific amount of intake. So there is a change. There is a change. So there will be change of the pressure, effective pressure of delta sigma t, and this d sigma t is basically now d sigma t plus dp, change of the fluid pressure also. Now, if it is so, if it is so, so the fluid pressure will act upward, total stress is acting downward, and effective stress is basically also upward. So this blue color indicates the water source in the aquifer. Now, the weight of the overlying water, weight, self weight, and the rock will remain same. Will remain same. This effective, the total weight of the water and total weight of the rock will essentially remain same. So the total change of the stress will be zero. So d sigma t is equal to now d sigma t plus dp is equal to 0 now. So basically d sigma t is basically minus d. It indicates that if T decreases, if T decreases, then the stress on the grain becomes greater. Or if fluid pressure is increases, reverse, the fluid pressure is increases, so increase and negative sign reverse. So basically, the effective stress acting on the grains will basically decrease. Basically, the increase of the fluid pressure will decrease the this pressure, and decrease of this pressure will increase this pressure. So this basically how the fluid pressure act on the grains and the grain matrix. Now it is clear.
Yes, sir.
Yes, sir.
Okay. Now the fluid pressure control the volumetric deformation. Okay. Fluid pressure controls the volumetric deformation. Now you see already earlier self weight and the overlying water weight is essentially remain same. So the change of the effective stress is basically is a change due to the fluid pressure. So how this fluid pressure can be measured and how can be represented? So fluid pressure basically controls the volumetric. So at a point P, rho GH minus rho Z is basically the pressure. Okay. The difference between the Z is remain constant, and the del P dP, change of fluid pressure, is basically, if I draw this particular diagram, do anyone know how to share two screens simultaneously? The pen screen is visible now?
No, sir.
Huh?
The
No, sir.
slide screen, sir.
The slide screen. Now the pen screen is visible.
Yes, sir.
Now the pen screen is visible.
Yes, sir. Yes, sir.
Rho GH minus rho GJ pressure at point. This is the difference between this a static one. Static one. So due to this, the change of the if it is a static one, then the change when Dp basically it will be H minus G. If it is static, the change is basically this term equal to 0. So dp is basically now H. This is what we have shown. Now the dp is basically now the d rho gh. Okay. So this basically is the effective pressure acting on the fluid and on the aquifer. So the effective sigma E is basically now minus d rho gh, that is the change of rho gh. Now if this pumping increase, see, it is due to the pumping process. It is due to the pumping process. The change is occurring there. If the pumping process increase, it will goes down. The pumping pressure, pumping is increased. Then this change will be high. This H will be high, basically very high. Okay. Then effective stress is goes up. You see, if the H is reduced, negative sign, so D sigma E is basically will increase. So effective stress will increase. And if it is go up, what will happen? We know in a confined aquifer we have already learned that. Now, how water is produced from a aquifer compaction? The aquifer cell compaction. So this compaction is basically change of volume, change of volume of the aquifer. So del V Vt, del Vt is basically the change of the volume, okay, and the original volume is Vt. So the ratio of the change and divided by del sigma E, change of the effective stress, is basically representing the aquifer compressibility. So aquifer gets smaller with the increase of the effective stress. So in the earlier expression, what we have seen, if the pumping is high, then the effective stress will increase. If the effective stress will increase, alpha will be very small. So the aquifer will get smaller and smaller with the increase of the effective stress. That is basically the relationship. And what about the relationship if water produced by the expansion of the water basically? Though we know that this water is incompressible, suppose this is not incompressible, fully compressible, okay. Then W is the volume, del VW is the change of the volume, that is the compressibility. So del VW divided by VW is basically the ratio divided by dP, change of fluid pressure due to this volume change, is basically the beta. The earlier expression we have already shown you the alpha and beta concept. Here we have shown you SS is basically is equal to rho g alpha plus rho g beta n. So this alpha is basically the compressibility of the aquifer and beta is basically the expansion of the water due to the compressibility. So VW, TVW is basically is equal to beta n rho g dh. Unit decline of the head, dh is equal to -1. So how it will be look like? VW is equal to plus Tn rho g, which is another component of SS. Okay. Now SS can be rewritten as rho g alpha plus beta n. SS is basically, if you take it into the bracket, rho g alpha plus beta n. So rho g alpha plus beta n is basically the specific storage in the aquifer. Now, the total change in mass with time is due to the change in density of the time. Change in density with time, term associated with the water compressibility. One. And second is change in porosity with time associated with the compressibility of the aquifer itself. And if it is so, then this equation will again come del Pn divided by del T is equal to N del rho divided by del T plus rho into del N del T. So our analysis where from the water actually comes will come from this expression SS is equal to rho g alpha plus beta n, and that can be replaced in this. Now, what are the dominant equations that we will actually use it? That is basically this. So del rho n is basically the change of the mass we are considering. So del px in the x direction, del rho qy in the y direction, del rho qz in the z direction. Basically, the qz is the amount and rho is the density. It is basically the mass. Okay. In x direction, y direction, and z direction. So rate of change of mass stored. Rate of change of mass stored is basically this. Same expression on the left side, it is remains same of the earlier expression. On the right side, we have replaced this and substituting this with the Darcy's law, pulling out K for a homogeneous and optional homogeneous material. So different K, Kx, Ky, Kz can be ignored and it can be rewritten as K and it can be rewritten as rho K del square H del x square del square H del y square del square H del z square is basically equal to rho pH del P en beta n rho g. Basically, it indicates the change of storage with the change of the head in time. Okay. Now, the storage term must convert into a volume produced by a mass produced. Multiply rho. Should multiply the rho, and we will get this SS dH dt is basically K del square H del x square del square H del y square del square H del z square. Okay, so this is the final equation for a flow in confined aquifer. In a confined aquifer system, storage rate index into del H del T is equal to rho gh beta n alpha. This is basically the SS. We have replaced this SS amount del H del T, the same amount, and the right side equation will also remains. Now, take an example how this confined aquifer system is working. So, water is released from a storage during a decrease of H head by two mechanisms. One by compaction of the aquifer caused by increasing effective stress. So, due to the reduction of H, effective stress will increase. Another is expansion of water caused by decreasing pressure. Expansion of water caused by decreasing of pressure. So this will give rise to the specific storage coefficient in two terms in the function of alpha and beta. Now, the compressibility of the material we have taken here. Clay is 10 to the power 6 to 10 to the power 8. Sand 10 to the power minus 7 to 10 to the power minus 8 meters per n, meters per Newton. Gravel 10 to the power minus 8, 10 to the power minus 10. A normal good quality rock 10 to the power minus 9 to 10 to the power minus 11. And for water, 4.4 into 10 to the power minus 10. So compressibility is very, very low compared to the other rock, the available rock we used. To do that experiment, where does the water store comes in a confined aquifer is basically this. This is a SS is equal to rho g and beta n taken. So it will come about the compressibility of clay 10 to the power minus 6. 10 to the power minus 6 the lowest value. Take Water from the storage, it will come around 0.0303. Sand 0.00694. Granite 0.00398 for a porosity of 30%. Uniform porosity we have assumed. Porosity distribution is uniform. So we have multiplied that. So it basically it indicates for a percentage of water storage for a clay, if it is media compression, it is so, and for a gravel, compression of the media is smaller compared to the clay. For a granite, compression of the water is high compared to the. For a more realistic porosity, porosities result are similar. Clay porosity 45%, gravel 35%, granite 25%. Compression it will be around 98% for a clay, gravel 39%, granite negligibly low. You see, granite is a very competent rock, so compressibility is basically negligibly low, only 0.9%. So basically, it is 0.09. The expansion of the water is basically like this. So total water will come for a granite is very small compared to the clay, in around 1, 10, 10 times. Okay. 10 times the clay water it is basically. So for this kind of system, for a homogeneous isotropic media, we will use the Laplacian operator like this: SS dH dt, basically K del square delta square H. This delta is the Laplacian operator. For a heterogeneous anisotropic, this can be rewritten as del Kx, del x, del H del x, del Ky del y, del H del y, del Kz dz, del H del z. Here Kx is equal to Ky is equal to Kz. Here Kx is not equal to Ky, not equal to Kz, because it is anisotropic. Means the hydraulic conductivity in x direction, hydraulic conductivity in y direction, and hydraulic conductivity in z direction is not equal. But all value is basically greater than 0. Greater than 0. All value is greater than 0. So for a 3D heterogeneous isotropic, it is for a homogeneous one, it is for a heterogeneous anisotropic, heterogeneous isotropic. So these basically del H, del X, K del A. So in place of Kx, same expression. In place of Kx, Ky, Kz, we have replaced this same equation with K only. Heterogeneous but isotropic means response in all direction, x direction, y direction, and z direction will remain same. So for a steady state, this del H and del T will be 0 for any equation. So basically, no water from the storage will come, and S value does not matter here. S value is not matter. So S is not a 0. This portion is 0. So that is why for a steady state, total is equal to 0.
Sir,
Ah.
sir, in the
Please?
past slide, sir, in the past slide, in this slide, del H by del T is equal to.
This
Sir,
slide?
next slide, sir. Sir, in this heterogeneous isotropic, del H by del T is equal to square bracket del by dx, sir.
Repeat the thing again.
Sir, here we have del H by del T is equal to square bracket del by dx or del x, sir.
No. This equation is fine for you.
Even though in this equation the numerator has del and the denominator has dx, na, sir.
Yes. No, this is del of this total expression. Del of this total expression. Actually, there should be a bracket. One minute. This equation should be rewritten as. If I use the expression. And it is basically the earlier expression is basically indicating the flow
Sir, I am just asking, sir.
this races del H del T basically del of del X of whole expression Kx del H and del X. Okay.
Okay, sir. Understood, sir. I'm just asking whether both the numerator and denominator have del or d, sir. There is some.
This is del. This is del.
Okay, okay, sir.
Okay. Now it is clear.
Yes, sir.
Okay. So for a heterogeneous, it is isotropic. This can be replaced in place of kx, ky, same k, and for the steady state equation, whole equation will be 0. Now for a confined aquifer, for a 2D flow, it would be looks like this. For this, it was 3D. Z will be removed. Z will be removed. So here del I square dx square del x square del x y square will be, and T is basically indicating K into B, that is the transmissivity of that particular layer, and T is basically the thickness of the aquifer, and SB and SS into SB also the storativity index, and T is the transmittivity index. This is the equation we will use time to time in the numerical simulation of this aquifer flow system. For a confined aquifer, heterogeneous anisotropic, this is the expression. Confined aquifer, heterogeneous isotropic, this is the expression. Confined aquifer, homogeneous anisotropic, this is the expression. So these equations will be solved using the differential simulator numerical difference finite difference method in different softwares that we basically use when we basically simulate the rainfall water scenario, how it is going to affect the stability of the slope. This is how in a slope how we calculate actually. Basically, what will happen if it is a slope, if there is a rainfall based on this, suppose this is a media, this is a slope. So how much amount will infiltrate UI? Okay, that we can determine how much amount finally will go out when it will face the porous media and this particular layer. So Q in and Q out, find out, and how much water will retain. How much water will retain? Retain means it is a storage. How much amount of water will retain? That is a storage. And due to this storage, what will be the development of H? What will be the development of H in this particular aquifer? This is what we simulate when there is a rainfall in a slope and how this is going to. So if H is redistributed, H is basically will exert OGH upward pressure. So it is basically is going to be reduced. Tau is equal to C plus sigma n dash tan phi dash also effective. So when there is slope stability, there is slope stability indicator analysis. So what we will analyze basically how much shear strength is reduced due to this saturation, new saturation, and how much the resistance it will offer and the ratio. This is what dynamically each iteration, we will calculate, and finally the solution has to be converged. Solution has to be converged. Based on that, we determine whether the slope will remain stable or the slope will fail. This is what we use this kind of flow system in different time. So this is all about the transient water flow system in slow mass. So now I request you all to raise your question so that one by one we can clear the doubt and we can proceed. Ajay,
Yes, sir.
any question you have?
No, no, sir.
Ashish,
No, sir.
Gabriel, 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 am I audible to you? Hari?
Sir, there are a couple of doubts for me, sir.
Okay, please tell.
Sir, please confirm that whether shale or sandstone which has the high hydraulic conductivity.
You tell first, I will tell you.
Sir, I am thinking that shale might have the high hydraulic conductivity due to the bedded plains it is having. But in books, it is that the sandstone is having the high hydraulic conductivity.
Yeah. Why it is so?
So, due to the presence of pores.
Now, you are asking why it is so.
Yes, sir.
Yeah. Remember, when they are considering shale as a rock, okay, sandstone as a rock, okay, it is not they are considering when they are giving it is a hydraulic conductivity of the shale rock mass, sandstone rock mass. That is not their concept. So when we are considering the hydraulic conductivity of rock mass, then only we will consider the layers, okay, that is the discontinuity planes, fractures also. What actually the reason, the cell composition, the grain size of the material is very fine. Whereas for the sandstone, grain size is relatively more. And if the grain size is relatively more, inevitably there will be more pore space. Suppose you take a marble of a radius 1 centimeter, diameter 1 centimeter. Take a marble of 2 centimeter diameter. Same volume, the pore space will be more for a 2 centimeter diameter marble. For this example, let me explain you. Suppose this is a very small piece of rock. So due to this small piece of rock, in between pore space compared to and for a similar one, pore space is more. pore space is, if it is a pore space is VP, and here is a VP. So this VP is basically less than this VP. Is understood, Haritarun?
Yes, sir.
So basically, it is basically the cell for a rock, and this is basically sandstone SS. Now the next question.
And so the next question is, sir, for example, I am working in a mine, sir,
Okay,
and it has benches of different heights, sir.
1 minute. You switch on your video also. We see your face also.
Sir. Is it visible, sir?
Not me, not to me. I don't know to others. Yeah, yeah, it is visible now. Please.
So, for example, I am working in a mine, sir, and it is having slopes of different heights, sir.
Okay,
And I propose to dewater the slope due to the high water pressure behind the slope, sir.
okay,
But there are many discontinuities in the slope.
okay,
And even though the presence of different discontinuities, I propose to dewater the slope, sir.
okay,
And now the whole slope is the water pressure behind the slope is reduced, sir, due to dewatering operations.
okay,
And then there is heavy rainfall.
okay,
So before the heavy rainfall, due to continuous mining operations, heavy blasting operations, those discontinuities are widened, sir.
okay.
Did you understand, sir?
Yeah, yeah, yeah.
After dewatering operations, the water pressure behind the slope is reduced.
Okay,
Due to continuous mining operations, those discontinuities are widened, sir, forming
okay,
tension cracks. Forming tension cracks, sir.
okay,
And then after there is heavy rainfall, sir, thus filling the tension cracks.
okay.
And there is I observed that the slope failure taken place, sir.
Yeah.
How do we deal with this kind of situation? And then after I observed that there is no use by dewatering the slope, sir.
So what process they have followed for dewatering the slope in that particular instance? Can you remember?
No, sir. I'm just imagining.
It's the imaginary case.
Yes, sir. It's an imaginary case, sir.
Okay, okay.
There is no use of dewatering the slope, no, sir.
No, dewatering is required sometimes due to different necessity. But actually, if you want to know the technical cause behind the failure, is it your questions you want to answer? You want to get the answer?
Yes, sir. And yes, sir.
And then
Sir, there is heavy rainfall, thus causing the failure, no, sir, filling the
yeah,
tension cracks.
yeah.
Then how do we respond to that kind of situations?
Okay. Very good questions. So this is a real time case scenario. How you deal with this kind of situation. So for this, few things we should remember. Okay. Few things we should remember that when we are dewatering in a slope, suppose if I draw a picture for this imaginary case, let me take few minutes time for that. So let me draw that particular slope. Suppose this is a slope. Now we are dewatering by pipes. We are dewatering by pipes. Dewatering by pipes. Above this level, it is not so much efficient. So these are basically the pipes. Suppose I am using a manual process to dewatering the slope. This will take time. This will take time. Suppose T amount of time it has taken. We have understood the efficiency of these drains. Now you are telling there is a precipitation. The precipitation was suppose 70 mm. Okay, 70 mm one day. Okay, one day. The precipitation 70 mm in one day, we can calculate the rate of rainfall. Suppose this is a Q mm or Q meter per second, we can calculate. It is per day means 24 hours to 24 to 60 to 60. That is second. So based on that, we can calculate this amount of rainfall is going to occur. We know the permeability of this rock. Suppose this is a homogeneous rock, I am assuming. This is Kx or Ky, all are same. So we know how much water is going to be accumulated in this water due to this particular rainfall. Suppose this rainfall, suppose for a one day, and you can also assume rainfall 20 mm rainfall for 2 hours, heavy rainfall suppose. Heavy rainfall for 2 hours and 20 mm. So after 2 hour rainfall, there is no other water. So due to this 2 hour water gets included in this layer, and the remaining water is flushed out of this water of this slope base. Okay. So 2 hour duration water will infiltrate, but that is not total. And we have already installed the pipes drain out the water, and we know the capacity of this pipe. Generally, the concept is the pipe capacity should be designed. It should be designed based on highest precipitation observed in that particular field. Suppose peak precipitation is Q max. Q max is the peak precipitation for a last 100 years of data. We know that. So ideal condition is to deal with this kind of situation. Pipe capacity, rate of draining out of the water, this pipe capacity should be high enough that due to this highest peak precipitation amount, what would be the net QI and what would be the QL out, QO. This Q out capacity should be designed accordingly about the pipe. And this can be handled in a real-time scenario. If we do that, then for a heavy rainfall scenario also, we can avert any kind of slope. So this is what technically the drain capacity determination can also be simulated, and you can do this using the programming. Suppose you can simulate same rainfall, heavy rainfall, and based on that you are increasing the capacity of the drain, and sometimes you will observe, even after heavy amount of rainfall, water gets drained out of that particular pipes and drain garland drain, and it is not going to reduce the factor of safety subsequent to a critical level that it will not. So by that method, you can avert the imminent slope failure due to the heavy rainfall. Is it clear?
Oh, okay, sir.
Mansi?
Yes, sir, it's clear.
Sanjeev?
Sir, for this lecture it's clear, but I have some doubt regarding assignment problem to calculate discharge.
Okay.
Because
So
I
actually,
didn't.
1 minute, Sanjeev. You can mail me separately because I have another class from 12. So we will discuss later, okay?
Okay, sir, tomorrow do we have a GeoMP test practically? Because so far we didn't get any mail.
Yeah, there will be test.
Okay, sir. And sir, timing we didn't get yet, sir.
Timing I will fix it today. Okay, I will think over it and I will fix it. Okay?
Because tomorrow we have that lab session, sir.
Yeah.
Okay. Thank you.
Thank you.